Okay, up to this point, we've talked about wave number and how wave number is affected by bond strength and the mass of the atoms in the bond. However, we haven't talked about the intensity of an absorption. And it says here that the strength or intensity of an IR signal or an IR absorption can vary. We can have a really strong signal like this that just absorbs a ton of infrared light. And then we can also have weaker signals like this one here. You can see most of the light was transmitted through the sample, so that means it only absorbed a little bit of infrared light. Well, why would that be? It has a lot to do with bond polarity. It says that here that when a bond undergoes a stretching vibration, it causes its dipole moment to oscillate. Right? You remember dipole moment? Well, if we look at, a carbonyl bond and a carbon-carbon double bond, which one of these has a stronger dipole? Well, of course, there's a much stronger dipole in a carbon-oxygen bond because oxygen is much more electronegative than carbon. There's a big difference in electronegativity compared to, excuse me, a carbon-carbon bond. There's very little different. There's no difference in the electronegativity of two carbons. However, since this carbon has two hydrogens on it, and this carbon has two methyls, they're in a little bit different of an environment. So there's a small dipole there. But the bottom line is that this is a highly polar bond, and this is a pretty weakly polar bond. Well, let's check out how that affects the absorption. It says the oscillating dipole moment makes a little electric field surrounding the bond. Okay, so you get this little electric field. Well, the more polar the bond, the greater the opportunity for the interaction between the waves of the electrical field and the infrared radiation. Put it in a nutshell, and what you need to know as a Chemistry 3101 student is nothing more than this. The more polar the bond is, the stronger the absorbance or the stronger the infrared signal is going to be. In our textbook, I think the way he puts it is he says that the more polar a bond is, the more it can act like a little antenna and pick up the signal of the infrared light. And I think that works as a very good way of remembering it. Check it out. If we look at the absorbances of the carbonyl, the carbon-oxygen double bond, and the alkene, the carbon-carbon double bond, you see that this is a more polar bond, and therefore it has a much stronger absorbance. This is a weakly polar bond, and therefore it has a pretty weak absorbance. So now you know about the intensity of a stretching signal in an infrared spectrum. Let's take another look at a compound that is completely symmetrical. This is 1,2-dimethyl-2-butene, this compound here, and we haven't learned how to name alkenes, but you see how this compound is completely symmetrical, totally symmetrical. Therefore, there's no dipole in here at all. No dipole whatsoever. No dipole. And if you're thinking, well, Mr. Dion, I thought you said there was a dipole between a carbon-carbon double bond. No, there's a dipole between them when they're not symmetrical, right? You see that we have two hydrogens over here and two methyls here. Therefore, it's not symmetrical this way. Okay, so that is why there is a small dipole. So that would mean that in this carbon-carbon double bond, it's implied that you have two different substituents here than you do over here, right? It's not symmetrical. Whereas if you have something that's completely symmetrical, no dipole, and therefore you see no absorbance around 1650, where you should see the absorbance for an alkene. Nothing. Okay, so just because you don't see the signal doesn't mean it's there. You can even have compounds that we call pseudo-symmetrical. Our book doesn't even get into these, I don't think. But let's say you have, I don't know, a carbon-carbon double bond like this. You go, that's a pretty bad bond. You got 1, 2, 3 methyls, and then you have an ethyl over here. Well, it's not symmetrical, but it's close to being symmetrical. And even this wouldn't really absorb in the infrared spectrum. Again, that's beyond the scope of our course. I wouldn't really worry about that a whole lot. It's called pseudo-symmetrical. Don't worry about it. Okay, so now we're going to get into everybody's favorite thing, intermolecular forces. I know that students love to talk about intermolecular forces or IMFs. Look, if I can make an advertisement for IMFs, let me tell you something. If you got half of the way or 75% of the way through intermolecular forces in General Chemistry 1, and you said, we'll need that again, Well, I can tell you the intermolecular forces come up in organic 1, they come up in organic 2, they're going to come up a heck of a lot in biochemistry. And so it's something that you want to make sure that you understand. And intermolecular forces are responsible for oxygen hydrogen stretching signals being quite broad. So we can have narrow or sharp signals like this one here, but you see that sometimes we have these broad signals that just take up a wide range of frequencies. Well, why would that be? Well, what makes oxygen hydrogen bonds so unique? Well, I can tell you what makes them unique. They can participate in what? Hydrogen bonding. You remember that wave number was directly proportional to bond strength? Remember that when we looked at that big old formula, we said that wave number was equal to 1 over 2. Come on, you get out of my way. 2 pi times the speed of light multiplied by the square root of F over reduced mass. Yes, we looked at that a few minutes ago. Well, it's coming up again because wave number is directly proportional to the strength of the bond. And what happens is that when an oxygen-hydrogen bond participates in hydrogen bonding, it can have an effect on bond strength. Check this out. When possible, oxygen-hydrogen bonds form hydrogen bonds that weaken the oxygen-hydrogen bond strength. Well, check this out. This is just a regular old hydrogen bond that you would have seen everywhere in Gen Chem 1 and in Chapter 1 of this course. But when you have that hydrogen bond, what it does is it causes the oxygen-hydrogen bond to just stretch out, really pulls it, yanks on that hydrogen. Well, if the bond is weakened, what's that going to cause? That's going to cause it to absorb at a lower wave number. Well, when the hydrogen bond kind of lets go too, it kind of snaps back like a spring in a way. And then you've got the oxygen-hydrogen bond is being really short. And then it's going to go back to its normal length, which is somewhere in the middle like that. So if it's really short, it's going to be really strong. And so what hydrogen bonding does is it causes stretching and changes the bond strength of the oxygen-hydrogen bond, which causes it to absorb over a range of wave numbers, which causes that broad signal. That is why we get all of these signals. Where it's up here, the bond is really strong. Where it's down here, it's really weak, but the average is somewhere in the middle, right? Hydrogen bonding causes those oxygen-hydrogen bonds to be pulled and stretched, which weakens them, and then they let go, and they get maybe a little shorter and a little stronger. Put another way, it says here on the slide, the hydrogen bonds are transient. And so the sample contains molecules with varying oxygen-hydrogen bond strengths, and that's why we get the broad signal. So we'll go from here to broad signal. All right. But, if there's one thing that you've probably figured out in organic chemistry, and my students always give me a hard time about this, there's always somebody who has to send me a meme about this, and it's true, is that organic chemistry is full of rules, but then what is it also full of? Exceptions to those rules. So let me tell you that there is an exception for the oxygen-hydrogen bond. If you have a solution of an alcohol and it's dilute enough, if it's really dilute, then there's going to be no opportunity for hydrogen bonding. And so in that case, you don't see a broad signal. Let me show you what you would see. If you have an alcohol that is really dilute, what you see is just a sharp signal because there's no stretching. So you usually see a really sharp signal. Let me get my ruler here. Around, what is this? Around a little bit above 3,500 maybe, 35 and a half, 3550, something like that. Okay, so this stretching is about, 3550 reciprocal centimeters. Whereas, again, if it's participating in hydrogen bonding, then it gets stretched. So again, we call that free hydroxyl because it's not hydrogen bonding. We don't see that a ton in Chemistry 3101. However, it's covered in your textbook. Thus, I'm obliged to show you. Whenever Dr. Klein shows you something, you can imagine it's pretty important. Well, besides an alcohol, so we know that alcohols can participate in hydrogen bonding. What other functional group did we learn in Chapter 2 that has an oxygen-hydrogen bond in it? Is there another functional group that we covered? Could anybody tell me? Is there another functional group that we covered that has an oxygen-hydrogen bond in it? Yes. Thanks, Angel. Katie, perfect. You're both 100% correct. My student said, what about the carboxylic acid, Mr. Dion? If I draw a carboxylic acid, it has a carbonyl in it, sure. But it also has an oxygen-hydrogen bond. So that means it's going to produce a broad signal as well. Check this out. Consider how the oxygen-hydrogen stretch for a carboxylic acid and how its wave number is around 3,000 reciprocal centimeters rather than 3,400 for the typical oxygen-hydrogen stretch of an alcohol. So out of all the functional groups that are recognizable in the infrared spectrum, the carboxylic acid is the easiest of all of them. And you heard me say the word easy. It is the easiest of all of them to recognize. There's nothing that is more recognizable than a carboxylic acid. Now, if you're wondering, well, why is the oxygen-hydrogen stretch in a carboxylic acid, why is it so huge? It is gigantic. You can see it's got this huge range. It's going from, we grab the ruler here, you can see it's starting around 2,500-ish, right? And then it's ending somewhere almost around 30. It means it's taking up 1,000 reciprocal centimeters of real estate on my infrared spectrum. Why would that be? Well, let me show you why. It's because a carboxylic acid can form this thing that we call a dimer. So this is a dimer. And the carboxylic acids align themselves in such a way that you have hydrogen bonding in two places. And it causes such extensive hydrogen bonding that it just stretches the heck out of those bonds. And that is why we get such a broad signal, because there's such extensive or pronounced hydrogen bonding in a carboxylic acid. So again, I don't like to use the word easy in organic chemistry, but I think that carboxylic acid is the lowest hanging fruit, so to speak, or the easiest thing for students to identify in a infrared spectrum. Okay, so we've covered the alcohol and the carboxylic acid. There's one more functional group that I want to talk about with you that can participate in hydrogen bonding. Out of all the functional groups that we learned in chapter 2, the alcohol and the carboxylic acid are the two that have oxygen, hydrogen bonds. But remember, in order to have hydrogen bonding, you've got to have a hydrogen bound to oxygen, nitrogen, or fluorine. Well, there's a functional group that we learned that has a hydrogen bond between a nitrogen and a hydrogen. What about an amine? If I have a nitrogen bound to two hydrogens, I call this a primary amine. And if I have an R group bound to a nitrogen with one hydrogen and another R group, so two R groups, I call that a secondary amine. And you can see that in the primary amine, we have two nitrogen-hydrogen bonds. And in the secondary amine, we have one nitrogen-hydrogen bond. And so since both of these have hydrogen bonds, they are both capable of having broad absorbances. But what do we know about oxygen and nitrogen? Oxygen has an electronegativity of 3.5, whereas nitrogen has an electronegativity of 3.0. Therefore, oxygen is more electronegative. Therefore, if we have a carbon-oxygen bond, an oxygen-hydrogen bond, it's more polar than a nitrogen-hydrogen bond. What did I say about bond polarity? I said that the more polar a bond is, the stronger the absorption will be. And so if we compare, an oxygen-hydrogen bond versus a nitrogen-hydrogen bond, this is going to have a stronger absorbance, and this is going to have a weaker absorbance based off of the difference in electronegativity or the bond polarity. Well, something else you need to know is that there's a difference between a primary amine and a secondary amine in terms of what you see in the infrared spectrum. Check this out. A primary amine, it says, will exhibit two signals for the nitrogen-hydrogen bonds. It's not because you've got two nitrogen-hydrogen bonds, it's because of the type of stretching. You can have symmetric stretching and asymmetric stretching. So here's my nitrogen, here's my two hydrogens, okay, here's my R group. So we can have symmetric or asymmetric stretching. Are you ready for Mr. Dion to act this out for you? Well, you better be, because I'm going to do it. So let me go back here, and I'm going to demonstrate the difference between symmetric and asymmetric stretching using myself. Okay, so chair back here. So let's imagine here's the two bonds. So this is one nitrogen-hydrogen bond, and this is the other one. This is a primary amine. Okay, so the bonds are stretching. Are you ready? You see two signals in the IR for a primary amine. Why? Because you have two types of stretching. You have symmetric stretching, where they're both stretching at the same time. So that's symmetric. And then you have asymmetric stretching. Is that good teaching or what? So symmetric stretching for a primary amine and asymmetric stretching. And that is why when we have an NH2, we see two signals. If you have a secondary amine, you only see one signal. And that's because you have one nitrogen-hydrogen bond stretching. Okay, so primary amine, you see two signals, symmetric and asymmetric. And for a secondary amine, you just see one signal. Everybody with me on that? I hope so. Let's go back here. All right, good, Kiana. Thanks. All right. Embarrassing, but hey, if it works, I'd stand on my head if I thought it would help. All right, so there you go. So let's take a look at what an infrared spectrum would look like for a primary or a secondary amine. So this is a primary amine. Primary amine. We see two signals here, and if you get out the ruler, we have one that's at about, so that's 35, 34. So one that's at about 33, and another one that's at about 34. And for a secondary amine, we have one that's at about 33, a little bit above 33. Anyhow, we're going to go over the table later on. So this is our secondary amine. But what do you notice besides the number of signals? Notice that they're kind of broad. Not as broad as an alcohol or a carboxylic acid because the hydrogen bonding isn't as intense. And then the bond isn't as polar. And so the absorbance intensity isn't as strong as an oxygen-hydrogen bond is either. And there we go. So that covers the shape of a signal, and we covered the intensity of a signal as well.